morning. We will wait for other students, and after a while, I will start. Good morning again. I hope you are all well and everything is well at your end, we can start. And let me share my files. Okay, this section is the last section of the last chapter. I mean, by this part, we can wrap up the chapters for dynamics in this semester. For this purpose, we will cover the linear momentum and angular momentum, and finally the conservation of momentum. By covering these three concepts, we can wrap up the chapters for this course in this semester. And for the next week and the week 14, we can have the revision sessions to review the previous chapters and get ready for the final exam and short test too. Okay. The linear momentum, the equations, and generally the relations, all of them are exactly the same as in the particles. Here, instead of the mass of the particle, we only have the mass of the rigid body. As you can see, the linear momentum defines m times by v, which g is the vector, and v is again vector, the vector of the velocity. But here the difference is that this vector is important, that this is the velocity of which point. We should note that this is the velocity of the mass center, okay? Because you know, when we have the rotation in a rigid body, the velocity of the other points will be different from the velocity of the mass center. But when we have the translational motion, the velocity of all of the points on the rigid body are the same. So this case, in the rotational motion may be different, but in the linear momentum, when you want to calculate the linear momentum, this is the linear velocity of the mass center. Okay, so you should note that this is the maybe the difference between the linear momentum for a rigid body and a particle. So according to this definition, you can use this equation, and if you want to substitute into the Newton's second law, you can extract the Newton's second law in form of the linear momentum, because we know that in the Newton's second law, the summation of the force is equal to mass times by the acceleration. In this equation, we have mass times by the velocity. So g dot, it means the first derivative of g with respect to time. If you want to extract the first derivative from this equation with respect to time, we will have m times by v, the derivative of m times by v with respect to time. M is a constant value because this is the mass of the rigid body, but v is not constant. So the derivative of v with respect to time, which is the acceleration. So you can see that this term, this g dot, in fact, this term is m times by acceleration. So we can write the Newton's second law in this form by using the linear momentum, and also the integrated form of this Newton's second law in terms of g, or the linear momentum. You can write that the initial linear momentum is the impulse during the period of time between t1 and t2. It's equal to the final linear momentum. So you can see we can use the integrated form most of the time in the impulse and momentum problems. When you want to use the impulse and momentum, we use the integrated form of the equation of Newton's second law, because in this form we have the impulse, and usually, as I told you, in the particles, usually in the impulse and momentum, we have a force in a very, very short period of time between, for example, T1, here you can see T1 and T2. So when we have a very short period of time, we usually prefer to use this equation to find the linear momentum, the final linear momentum here, G2. And when you calculate the final linear momentum easily, you can find the velocity here, the velocity vector. So we prefer to use this form, the integrated form, because the first form, this one, in fact, is the Newton's second law. And if you want to use this form, you need to obtain the acceleration, the summation of the force, and then find the velocity and in terms of the acceleration by using the integral form, or you need to some kinematics relations. But here in the second form, you directly can find the velocity from the external forces. So the procedure to solve is exactly the same as the particles, only there are some points, such as here we have the velocity of the mass center. So from this equation, the integrated form, if you extract any velocity for each point, this velocity is the velocity of the mass center. And if you want to find the velocity for other points on the rigid body, you need to use the kinematic relations, the relative velocity equation, and find the velocity for other points. And also, again, this point, we can write this equation in the scalar form. The scalar form, you know, because, for example, if we assume that this is in a Cartesian coordinate system, we can expand this equation in a scalar form. And in the scalar form, we will have, for example, the summation of the force in x direction is equal to the linear momentum in x direction, and in y and z you can write as well. So you can expand this equation, and also the integrated form, this one, you can expand this in the form of the scalar form, and you can write it in different directions. The next concept is the angular momentum. Again, the angular momentum is similar, the equation is similar to the particles, but this time the angular momentum is equal to I bar times by omega. In the particles, when you calculated the angular momentum, it was omega cross, um, it was, for example, for a particle with mass m with radius r, it was r m omega. And in this case, in fact, in the particles, instead of this I bar, or the mass moment of inertia, we had the mass moment of the particle about the that point that you calculated the angular momentum. But here we usually write the angular momentum about the mass center. This G means the mass center. So the angular momentum about the mass center is equal to the mass moment of inertia about its mass center times by omega, which is the angular velocity of the rigid body. So this is a difference again between the angular momentum for a rigid body and the angular momentum of a particle. So the equation is a little different, because for a particle, there is no mass center, because a particle does not have any dimension and its position is exactly its mass center. Okay, so, but for a rigid body, when we have dimension, we have another concept, which is the mass center. So usually we write the equations about its mass center, but also we can write the angular momentum for a rigid body about any other points, any other point than its mass center, and you will see how we can write this equation. Again, if you write the, if you use the integrated form and the Newton's second law, and its integrated form, you can extract the moment angular momentum equation. This is the moment and angular momentum equation. And this is the integrated form. Okay. Again, similar to the linear momentum, we will have the same scenario. We have the summation of the moments about the mass center. It's equal to the first derivative of angular momentum with respect to time about the mass center. Again, the angular momentum in initial position or initial condition, it's equal plus the angular impulse moment is equal to the final angular momentum hg sub 2. So again, from this integrated form, similar to the linear momentum, you can extract the angular velocity directly from this equation using the relation between the moment and the angular velocity. Okay, so again, in this chapter, we usually use this equation to extract the angular momentum in final position and the angular velocity in final position, in fact. And again, this hg, you should consider that when you are calculating h, this is about the mass center, and you need to calculate the mass moment of inertia about the mass center. But sometimes we need to write this equation about any other points other than the mass center. And another point here, which is mentioned, because angular momentum vector is always normal to the plane of motion, vector notation is generally unnecessary. So here in the previous slide, if you look at here, we don't use the vector notation because there is no difference, because we know that the direction is always normal to the plane of motion. So in angular motion and angular momentum equation, it's not necessary to use the vector notation because only there is one direction. Okay, so this is the angular momentum equation. The summation of the moments about the mass center, this term about the mass center of all forces, all external forces, is equal to the rate of the change of angular momentum about its mass center. And if we want to define the physical definition for the integrated form, you can see that the initial angular momentum about the mass center plus the external angular impulse about the mass center again is equal to the final angular momentum about the mass center. So it's very important to note that all of these equations are about the mass center. But as I told you, sometimes we need to write the angular momentum about any other points other than the mass center. For example, here, consider we want to write the angular momentum about point O, which point O can be either on or off your rigid body. So HO is equal to the mass moment of inertia about the mass center times by omega plus mv bar d, which again v bar, this term is the velocity of the mass center, m is the mass of the rigid body, and d is the distance between point O and G. You can see it's similar to the when you wrote the equation, the Newton's second law equation about uh, a point other than the mass center. For example, you calculated the moment about point O, it was equal to exactly this term, something like this. Of course, instead of omega in that equation, we have alpha, and instead of v bar, we had a, which of course a bar, the acceleration of the mass center. So here you can see this is the angular momentum about about the point O, which O is not the mass center. And sometimes we have the pure rotational motion, again similar to the Newton's second law equation when we had the summation of the moment about point O, which point O, when it was the fixed point of the rotation, it was equal to IO alpha. Here we have that HO, the angular momentum about the point O, which O is the fixed point of rotation, is equal to IO, again mass moment of inertia about this point, times by omega. A simple example for this case that sometimes we use is again the rotation without a slipping. You know, when we have rotation without a slipping, for example, when we have a wheel on a surface, of course, better. When we have a wheel on a surface and it's rotating without a slipping, exactly at this point here, we can assume that this wheel is rotating with a pure rotational motion. So if you want to find the angular momentum for this wheel, the angular momentum equation, if we call this point O, you can write that HO is equal to the mass moment of inertia about point O times by omega. So when we have a wheel which is rotating without slipping, we usually prefer to write the equation about this connection point, because this is like a fixed point of rotation. And finally, the angular momentum equation about point O. If you want to extract this equation in the first form using the Newton's second law, as I told you, it's equal to the moment about O is equal to H dot O, which H dot O in fact is I O, or the mass moment of inertia about O, times by alpha. Instead of omega, we will have alpha. And this is the equation that we used in previous section. But we use this form again in this section, the integrated form, which uh, states that the angular momentum about point O in initial condition plus the impulse momentum about point O during the period of time t1 and t2 is equal to the angular momentum about point O in final position. So again, we use this equation, you can see, but in this equation this time, MO is the moment about point O, moment due to the external forces. HO is the angular momentum, this term, about point O, okay? And O is the fixed point of rotation for this rigid body. So this is the all the equations that we need in this chapter to solve the problems for angular momentum and angular linear. And the last concept is the conservation of momentum, exactly similar to the particles. Again, here we have the conservation of momentum for a rigid body. If the summation of the force, the external force, was equal to 0, we can conclude that the linear momentum will remain the same, and there is no change, and initial and final linear momentum will be equal. And for the angular momentum, we have the same. I mean, when there is no external moment, or the summation of the external moments about a point O, or about the mass center is equal to 0, we can conclude that the angular momentum in initial and final position must be equal, and there is no change in the angular momentum about point O or about point G, which point O is the pure rotation. This is the fixed point of rotation, and G is the mass center of the rigid body. So this is the all concepts, and this part is exactly similar to the part for the particles, but you should consider that in this part g1 and g2, when you are calculating them and you are calculating the velocity in this equation, the velocity extracted from this equation is the velocity of the mass center. In these cases, HO1 and HO2, when you are calculating HO1 and HO2, you need to find the mass moment of inertia about 0.0. But for HG1 and HG2, you need to calculate the mass moment of inertia about point G, which is the mass center. Okay, clear? Any questions so far? Okay. Okay, we continue with one example. Here, the mass center G of the cylinder bar of mass 0.8 kilogram and length 0.4 meter is falling vertically with a velocity of 2 meters per second. At the instant depicted, calculate the angular momentum HO of the bar about 0.0 if the angular velocity of the bar is part A is equal to 10 radian per second in clockwise direction, this one, and part B, the angular velocity is 10 radian per second in counterclockwise direction, this term. So we have two different angular velocity. The value, the amplitudes are the same, but the directions are different. We want to calculate the angular momentum about this point O. So which equation is suitable for this example? If we back to the previous slide here, which of this equation can be suitable for this one? Definitely, we don't need to write the angular momentum about the mass center. Yes, we are calculating the angular momentum about point O. If we call it equation 1 and this one equation 2, which one is suitable to use for this example? Why equation 2? Is the body rotates about a fixed point in this example. Here you can see when a body rotates about a fixed point O. In this example, is the point O a fixed point of the rotation? So which one? 1 or 2? The equation 1 is the angular momentum about any point O. So this is an arbitrary point. But equation 2 is for point O when a body rotates about a fixed point O on the body. Is point O a fixed point in the example? This point O is a fixed point. I mean, When this cylinder is coming down, still point O is a fixed point of rotation. First of all, a fixed point of rotation must be always on your rigid body. As you can see in this slide, here it is mentioned, a fixed point O on the body. So you can see a fixed point is always on your body. For example, as I told you, when we have a rotation without slipping for a wheel, when we assume that the connection point is the fixed point of rotation, that connection point is a point on your wheel. So you can assume that this point is a fixed point of rotation. But here, point O, first of all, is not on your rigid body. This is the cylinder. Point O is not of its rigid body. Maybe it can be an instantaneous center of zero velocity just for this instant, okay? But after that, it's not the center of rotation, okay? So point O definitely is not a fixed point of rotation. This is only a point, an arbitrary point in fact, and we need the equation 1 to use and find the angular momentum. Okay, so when you want to find the angular momentum about point O, because point O is an arbitrary point, it's not the fixed point of rotation. As I told you, maybe it can be the instantaneous center of zero velocity, okay, but it's not a fixed point, okay? So we cannot use the equation 2. Is it clear? Did you get it? Is it clear now? Okay. So now we use the second equation, as I told you. Sorry, the first equation, I'm sorry. This is HO, as you can see, the angular momentum about point O. So we need to find the mass moment of inertia about the mass center times by omega plus mv bar d. D is the distance between the mass center here. D is the distance between point G, as you can see, and point O, which is 0.3 meter. Okay. V is the velocity of the mass center. This is the velocity of the mass center, V. And M is the mass of this body. So HO in part A, because omega is this case, the clockwise direction. So the moment due to this omega is clockwise. We assume that, for example, the clockwise direction is positive. So omega will be positive. As you can see here, we substitute omega is equal to 10 radian per second. We have the I bar, which is the mass moment of inertia about the mass center. For a slender rod, we know it's equal to 1 divided by 12 times by ml squared plus mv bar d. And again, m is the mass, 0.8, v is the velocity, and times by d, which is this length, 0.3 meters. But for part B, we know that the direction of the omega is in counterclockwise. So we assume one negative. We have one negative here. And when you substitute here in the equation and simplify, this term will be negative, but again, mv bar d is positive because the moment, the angular momentum due to the velocity, linear velocity, is in clockwise direction. So we use the equation 1 to obtain the angular momentum about point O. Is it clear? Any question? Yes, d is always given because here you can see d is a distance. In fact, when you are finding the d, you can assume that your v is a force. Okay, you can assume vector v. Here you can see the v is a vector, a force vector, and you want to calculate the moment due to this vector about this point O. Okay, so you need to find its arm. D is that arm. You need to calculate the arm of this vector about point O. Here you can see v is in vertical direction, so its arm is 0.3. If v was in this direction, for example, then d was this length, this vertical distance. Okay, so d is similar to an arm for calculating the moment, but here it's given, and usually d is given. D is the distance between the point mass center and the point that you are calculating its angular momentum, point O. And you should consider the, in fact, it's similar to the arm. Okay, so it depends on the direction of v and also the position of O and G. Clear? Okay, if you don't have any question, we can wrap up this session and continue again tomorrow. No question?